everyone, welcome to Baozi Training Leetcode solution. If you want the best mock interview in North America, feel free to check us out at baozitraining.org, where we can help you to land your next dream offer. So here today we're going to talk about this question in Leetcode. Add and search word. It's a data structure design question, but also it's kind of a coding question. Essentially, what you wanted to do is design a data structure that supports add a word. Each word is a string, and then you can also search the word. One little bit interesting part is, so you read it here, okay, so all the letters containing only letters A to Z or a dot, comma. A dot means it can represent any one letter, so it's basically, it has to be at least one and only one letter. And then just note this example, right? So if you have a word bad, dad, mad, you added it there, and then when you search this word, it will return whether true or false. But this the dot can represent any letter. So in this case, like B dot dot could be BAD. And also note this only supports strict matching in a way that, let's say if you have the word BAD, but if you're trying to search for BA, because it doesn't really contain the word, even though you match is the prefix, it doesn't count. So this is some good clarification question you want to ask in a real interview. And then here's the thought process. So for this one, because it's matching from the beginning to the end, strictly matching, so it's kind of it's a string matching problem, but okay, this is more like a strict matching. So a try data structure, essentially a prefix tree, will come in very handy versus something like a suffix tree. This is more like a pattern matching that can match any strings. Any patterns in the string, so instead of from the beginning to the end. So familiarize yourself with the try data structure. It is actually very, very simple. So I would expect the candidate should be able to write a try data structure with the add and search very, very quickly in real interview. So this is basically a try data structure. So it is actually a root, and then you can, for each of the one node, you can actually create a node, and then you link them together. Once you insert a node, for example, you have a GEEKS, that's one word, and you can have GEEKT, that's another word. So what I personally like to do is, I'll show you later in the code, is I'd like to create a kind of like a notation of each of the node, whether it's an AND or not. So let's quickly talk about this try node. So each one, of course, will contain a character. So I personally like to have a node that is called its AND. So essentially what this means is this is actually the end node of the word. So without this, you can also doable. It's also doable. You essentially just check the children whether it's empty or not. But this is just more clear and explicit. I just personally like this way to code so that I know when I do pattern matching whether I hit the end of the node or not. And then another way is basically here we need for each of the node we need to carry what's their children node. So I use a hash map. You can also use let's say an array of 256 of all the ASCII2 word. That will also work. I just use the map for now. Yeah. So once you have that, the search is also kind of obvious in a way that, let's say if we don't have the dot case, you literally just map one to one. So you have for each of the string you want to match. Let's say you want to match G, E, E, R. You check G, you check E, you check E, you check R. Let's say you want to match G, R. You check G, and then you check R. Oh, there's not any children there, so we return false. So the tricky part is with this dot. So essentially what we can do is more like a DFS way, right? So if you have a dot, that means you have to, that can represent any string. So that forces you have to explore all the possible search paths, which is, let's say this one is GEE dot. So you have, let's say it's GEE and the dot, right? And then that dot could mean all of these three. So that means you have to explore all the paths of the three recursively. So that's a very simple DFS solution. So I will talk to the code now. Okay, this is a class. We have a constructor, a new dummy root, and then whenever we add word, we do some sanity check, and then we have this insert helper. So this insert helper essentially is just, keep adding the node. If this equals to the length, that means it's already at the end. So we just put the node end equals to true. Or else we just keep adding each of the characters, so by calling the insert helper. If it contains key, that means you don't want to create a duplicate key, so you just keep going. Or else you want to create a node, assign the value of the character and then put it into the hash map and then continue adding it recursively. Well, you can think about it as recursively, but essentially it's basically straightforward ON, and in terms of the word length. And then for the search method, okay, sanity check, and then we use this search mapper. So essentially what it does is, so remember, once you reach to the end of the word, this is kind of the edge case I call it out. It has to be strict matching. So as long as you reach to the end of the word, everything works fine previously. Then you still need to know whether this is in your try, whether this node is the end or not, or else you are only matching the substring. So that's not what we want. And then if it contains node, that pretty much, if it doesn't contain the node, then we'll do the check. If it doesn't contain the word, we can directly return, or else we continue. Else, if it's actually a dot, that means we have to explore all the possible paths, right? So essentially what we do is for all the children, we recursively call this, and for the next one, right? And for the next character, that's why it's index +1. So if any of those matches, we just return true, else we return false. So the interesting part is basically the time complexity. I will spend a little bit more time on this. So the add word basically is very straightforward, it's ON, and it's the length of the word. And for search, what's the worst case, like time complexity? So it's actually OM in terms of M, in terms of the entire try space, that is the total number of try nodes. So think about this case, right? A worst case, like we have so many dots. So each of the dots can match any string. So on a high level, if you close your eyes, you can think about, okay, this has to travel through all the tree space. So let's say n is length of the word, and then the depth of the tree, let's just assume is, so if you want to analyze like step by step, let's say n is the length, and then the total number of nodes we traveled is n times basically nodes on each try's level, right? How many nodes? So let's assume there's m nodes, and then let's just assume the try's height is kind of like a tree, right? The tree's height is log m. So this is right now is the total nodes we're going to travel. And then for the worst case, n will basically equals to the longest. It's like the longest word we have seen so far. So that pretty much is a try's height. That is log m. So this becomes n times m. This becomes, because n equals to log m, this becomes this, and it equals to m. So that's pretty much is the total space for total time complexity. And just remember, there's also, you can compress the try a little bit by shifting up the nodes. So you can Wikipedia that, but this space analysis still holds true. For the space part, I mean, adding a word is on in terms of how many nodes are there, and is basically the character is essentially that's the new nodes you're going to add. But not is like but if the node already exists, I mean, you don't need to add it again, obviously. And the search, there's no additional space needed. Here I want to mention a few follow-ups. So just think about it here. I listed all the solution. So instead of matching the dot, how about you matching a wildcard, a star sign, which means it could be empty and could be any kind of string. And how do you remove a word from the try? Let's say right now I want to remove something from the try. How do you count clearly that you only remove it when nobody else is referencing it? Just think about that. Okay, all right, that's all. Thank you very much for